much. Definitely want to thank everyone for sticking it out all the way to 4 p.m. on the last day. So is anyone else a little worn out from the week? I know I am, but I do appreciate everyone being here. I do want to talk about kind of high quality qubits. So I would say, IBM took a slightly different approach than we have. I don't think either one's right or wrong. I think it's just a different approach where they talked about how they're scaling very quickly, and now they're focusing on more of the quality that they need to be able to do all of these gates. I think from Quantinuum's perspective, we've been very focused on producing really high quality qubits, and then scaling's been secondary, but we are scaling as we go. High quality qubits are so important because it really dominates what you can do today on quantum computers, but you also need really high quality qubits to get to that fault tolerant quantum computing future, right? So here I've kind of broken it down to these two different regimes where you could operate your quantum computer. On the left, it's, you could call this the NISQ era, right? You're running the applications directly on the physical layer, directly on the physical qubits. That's where your logic's happening. And there, I think, I put down some goals. These are kind of a little bit flexible and arbitrary, but there are reasons I picked these numbers. So I picked 99.99% fidelity operations for two reasons. One, because I think we can get there in the next couple of years. I really do think we can get 2-qubit gates at 99.99%. And two, I think at that point, maybe there's a little bit of diminishing returns as far as what it buys you for overhead for a fault-tolerant quantum computer, and you might use your efforts somewhere else more efficiently. And once you have that 99.99%, that kind of sets the scale of how many physical qubits you want to kind of be in the hundreds. I think if you have many, many thousands, you're not really increasing your computational power if you're really doing the applications on the physical layer, right? Now, of course, there'll be an in-between where you start doing some error detection, you start maybe doing some lightweight error correction that's not fully fault tolerant, and there will be the need and the desire to have machines operating there, but it seemed like a reasonable kind of goal on the applications on the physical layer. And then when you go to the right, you start thinking, okay, now we're not going to operate on the physical layer. I need thousands of logical qubits, which would create maybe millions of physical qubits would be needed to create those. And now you're going to drive those errors to where I don't want to write that many nines, so I go to scientific notation and talk about errors, and down to the 10 to the minus 12 level, let's say, which is a reasonable level because of many challenging applications would kind of require this sort of quantum computer. But the point is that high quality is needed for both of these regimes. Certainly 2-qubit gate error matters, and that's a big part of the quality, but that's not the only thing. And so I'll talk about some of the other things we need in our high quality qubits. And you'll see there's strong overlap in these two things. These are not at cross purposes, these two goals. It's not perfect overlap, but there's strong overlap. So now I'll just talk about where we are kind of on that physical layer. And this is a picture of the H2 ion trap. So we just released our H2 system this spring. It's available now. Customers are using it. This is a photo where it's a surface electrode trap. So it's made in silicon microfabrication facilities. It's a very scalable trap technology. It's kind of got this oval racetrack shape. And here we have 32 qubits, which is where we launched the computer at. And they're transporting around, so each dot is an individual atomic ion of ytterbium that we're shining a laser on. It's fluorescing, and we're capturing that on a camera. So again, this is not a simulation. This is real data from a camera. So it's really cool in quantum computing to be able to control these things at the atomic level and control their quantum properties. And this is kind of just going around the racetrack in kind of the Daytona 500 mode, I would say. We can actually do more complicated ion transport dances. This allows us to actually arbitrarily connect the ions together, which is another part of what high quality qubits, what something you're looking for is. I will announce that this will be extended to over 50 qubits in 2024, so that puts us in this regime where brute force classical simulations no longer work, right? If you do a full state vector sim or something. So that'll be an interesting regime. So here I just want to talk about a few of the high quality qubit features and then how we benchmark them and kind of where we're at, right? So the first one is arbitrary connectivity. So that's just a little diagram of 32 circles for our 32 data qubits. And there's a line between each one, and in many architectures, you would need a physical wire to go between them. There's, I think, 496 of those wires for all of the pairings here. In our architecture, we do not need to do that because we can physically move the ions, right, and connect them in that way. So this is very important for near-term applications on the physical layer. Your application usually is not nearest neighbor connected, but it's maybe a little less clear to see that it's actually very useful potentially for getting to a fault-tolerant quantum computer. There's been some mention of LDPC codes, and many of them require a higher level of connectivity. There's no real a priori reason to believe that nearest neighbor connectivity will give you the best error correction code, right? So we might be able to, with much fewer physical qubits, get to the same number of logical qubits by using this connectivity, even in the long term. Another feature is parameterized 2-qubit gates. This is used in our systems now. This is one where I'd say it's very clear it's useful on the physical layer. It's less clear it'll be used in the fault-tolerant future. This allows you to do less than fully entangling gates. We use it almost in all of our internal demonstrations these days. But even in the fault-tolerant future, you certainly need low error gates because, again, that can lower your threshold of physical qubits to get a logical qubit. And the last one I'll mention is another really critical one. It's mid-circuit measurement and resets. So this allows qubit reuse on the physical layer, and we're developing algorithms that use this heavily. But it's really critical for fault-tolerant quantum computers. There's really, most architectures require this, and it needs to be at really low error rates. So then how do we benchmark the qubits? How do you know they're high quality, right? So we have kind of three flavors of quantum computing benchmarks I'll talk about. The first one's at the component level, so think single qubit gates, 2-qubit gates. The next one's at the system level, but maybe it's complex, but usually kind of random operations, so something like quantum volume. And then the last one's applications. So do some form of application that you can use as a benchmark, like Hamiltonian simulation. And the day we released commercially the H2 system, we made this archive of paper available online. It's now been accepted in PRX. And it had all of these benchmarks in that paper, including the component level, the system level, and the algorithmic level. And then I'll talk a little bit about logical circuits. That wasn't part of the paper, but I have some data in here that will be made available publicly soon. So I'm going to fly through some of this so I don't run over time. But all of this data is in this archive paper, so you can go online and find it. And we also have a GitHub repository with raw data and so forth. So this is some of the representative data. So you have single qubit gates, 2-qubit gates, state preparation and measurement. So you can see our 2-qubit gates are at 99.82%, and the state preparation and measurement error is also down in the 10⁻³ level. The arbitrary connectivity, one way we kind of benchmark that is you can think, well, there's a cost to that, right? The cost is it takes time to move these ions around. You could potentially cause errors in a number of ways. For us, the main cause of error is just the time it takes. Gives you some memory error because you have a finite coherence time. And so we benchmark that by looking at what we call the error in the depth 1 circuit time. The depth 1 circuit time is just defined as I have 32 qubits. You give me an arbitrary pairing of those 32 qubits, whatever you want. I rearrange them such that they're paired with the right partner, and then I do a 2-qubit gate across all 16 pairings. And that time in H2 right now is about 50 milliseconds, and the error we accumulate is 2e⁻⁴, so it's about 10 times smaller than the 2-qubit gate error. We also have this parameterized 2-qubit gate, and one of the really nice things about it is as you go to less than a fully entangling gate, you actually get less error. It goes kind of linearly in this angle with an offset that's about 5 e to the minus 4. I think we can, through work, make that smaller. And then this mid-circuit measurement and reset. So there, the biggest error, of course you have error, the measurement error of the qubit you're measuring, but then you worry about, do I impact the other qubits? And so that's the crosstalk piece, and that crosstalk for us is down at 5 10 to the minus 6, so extremely small errors. So really what you need if you want to do fault-tolerant quantum error correction. Okay, so then we go to the system level performance, and we use lots of other people's metrics. We're happy to use other people's metrics. So IBM introduced quantum volume. The H2 released it to the 16, something like 65,000. Mirror benchmarking was introduced by Sandia National Labs. This is where you run a kind of random circuit, and then you do the inverse so that you can quickly and easily compute what the answer is. So it's a more scalable benchmark. This is one that I think we'll see more and more in the industry, I hope. And then Google introduced the cross-entropy benchmarking fidelity, where they're doing this random circuit sampling. We show that for up to 32 qubits at very high fidelity. Then you move into the applications, and we did Hamiltonian simulation. We did quantum dynamics, where you actually perturb the system and see how it evolves over time. And this was using mid-circuit measurement operations. That's an example of using mid-circuit measurement at the physical layer. And then we started demonstrating logical circuits. And all this time, we're also improving the H1 system. The H1 and H2 systems share the same lasers, the same qubits, ytterbium-171. So as we make improvements on H1, we will be able to port them over to H2. It's just a matter of timing. Recently I've seen in this forum, but a lot of other forums, people say, well, the current state of the art's 1 error per 1,000 operations, right? That's a standard thing to say. It always bothered me a little because we never have actually been there commercially. We just made some recent improvements. This is data from a few days ago. It was at the 99.894% level, so I wasn't ready to declare victory yet. But just yesterday, I haven't had a chance to update this slide, but we're actually at 99.9% now. So we can say, people have commercially run yesterday and today. So we're actually at the point where we are at 1 error per 1,000 operations. So with the H2 release, we were really trying to be kind of setting a trend of putting out the data during the commercial release so that you can really see how the machine operates right out of the box. Now I'm switching gears a little bit and talk about that fault-tolerant error, right? So how do we get there? How the quality of the qubits kind of impact things? And how am I on time? Okay. So I'll have to be pretty brief on all of these, but because we have these high-quality qubits, we can have a very versatile quantum error correction testbed, right? So that's allowed us to do multiple quantum error correction codes and to do many experiments on them. The first one I want to highlight is data from a few years ago, but it was the world's first demonstration of really real-time decoding, which again is something you absolutely have to do if you want to get to a fault-tolerant quantum computer. I would say to this day, it's probably still the best demonstration of this. This is with a color code, and we're doing multiple QEC cycles. There's been a lot of talk about higher efficiency codes using more exotic LDPC codes. Here we're starting to do experiments there, and again, because of the high qubit connectivity, this was data from a 1224 code, so it's able to correct one error and actually detect a second error. And we see we're beating the physical memory error, which is, the coherence time is very long out of the box. It's several seconds. But we can even do better by logically encoding our qubits. It's a very efficient code because you have 2 logical qubits per 12 physical qubits, so only 6 qubits per logical qubit. So that's all single qubit stuff. So what about taking logical qubits and actually entangling them, right? So this is work from 2022. We encode two logical qubits in the Steen code. It's a color code. We can do logical rotations, and then we do a transversal logical entangling gate between two logical qubits using this transversal gate, which requires, again, all-to-all connectivity. We can add QEC cycles, and then we can measure it out. So the interesting thing here is, well, first, the fault-tolerant spam beat the physical spam by an order of magnitude, right? So here the logical encoding is actually helping you. And then I think even more impressively, you do the circuit where you logically encode, you state prep, you do your 2-qubit gate, and then you do measurement. That circuit at the logical level was actually beating the physical level. So those numbers are highlighted there. You know, we didn't call this a break-even moment because when you add QEC cycles, it actually decreased the fidelity and you were below the physical limit. But it was still a really neat moment, and I think that's another thing that's kind of next on the list, right? Now you want to move beyond that and start running actual circuits at the logical level. So here's a quantum Fourier transform, where now all of this circuitry is done at the logical level. With the caveat, you know, we're using a non-fault tolerant state injection, but we were still able to, you know, start to measure at the logical level, kind of a subroutine that would be useful long term. And another example of this is we took, you know, we call this the iceberg code because that little diagram looks like an iceberg for some people, I guess. And we're able to logically encode a 16-qubit GHZ state. This is a very high efficiency code, again, using the connectivity. And we're able to improve the physical fidelity of 91% to 98% logically encoded fidelity with a 40% discard rate. And the last thing I'll mention, I don't have time to go into any detail, but I do encourage people to take a look because I think it's really beautiful work. There's some really nice popular articles about creating these non-abelian anions for the first time ever and braiding them. And there's also, you know, a scientific paper that has all the nitty-gritty details for the experts. And with that, I will end and thank you for your time.